Welcome to our first Technology Day. There were so many things to show at EK Expo that we wanted to take time to point out the technology behind them. And here it is. Technology Day is all about the technological advancements, processes and driving forces behind our innovations. Basically, how we're shaping the future. Eddie, welcome to the stage.
Right now is an exciting time to live. Computer advancements, artificial intelligence, and all of their possible applications shape entirely new enterprises and technologies. But there is one limiting factor that we predicted would be significant for the future of computers: liquid cooling. And we are right, but only partly. As the demand for computational power exceeds any improvements to efficiency, computer must continuously deal with their thermal challenges to deliver higher performance. Power limits of some chips can be raised as high as 600 watts with software alone, so cooling is the only thing holding them back. But outright performance is not the only challenge. Sustainability, for example, is becoming a major consideration. We cannot neglect the wasted energy that could be put to good use elsewhere, as well as of course doing everything we can to minimize consumption in the first place. It's a complex problem, so it requires a significant consideration. As the biggest liquid cooling provider, EK is working on several innovative solutions, which we will discuss in detail throughout the event. It's about technology, and some more technology. So join our team as we highlight the challenges we face and elaborate on our solutions. But enough of intro, let's see how increasing computing power correlates with temperature. Blaž, the stage is yours.
Thank you, Eddie. Yes, the main driving factor in technological advancements in computer cooling is, in essence, more computing power creates bigger demand on the cooling system. There are differences in efficiency from manufacturer to manufacturer, but what basically boils down to is more oomph, more heat. When dealing with heat, it is a relatively established general fact that the performance of liquid cooling is superior to air cooling. If we just look at cars, we do not see any of the major brands using air-cooled engines anymore. Even those who were using them the longest, as it was part of their heritage, abandoned the technology more than 20 years ago. And liquid cooling in computers is nothing new. It's been around basically as long as they have. Some data centers from the 60s that we consider to be the start of modern computer were already liquid cooled. IBM System 360 Model 91, which was used by NASA, was one of them. And it was one of the most powerful computers at that time. It could perform 16.6 million instructions per second and had 4 megabytes of memory. That is, however, several thousand times less than today's mid-tier phones are capable of, let alone a modern supercomputer. However, even in those early years, the superiority of liquid cooling was well established regarding heat transfer and dissipation. But as it is more complex, and the large size of those computers allowed for sufficient heat sinks and airflow, the classic approach of air cooling was still the most popular option. In later years, there were a few examples of liquid-cooled systems here and there, with the only major breakthrough being a new approach of cooling by immersing the whole computer into a non-conductive liquid. But as energy was cheap and few performance gains could be made, liquid cooling was still a novelty rather than the norm. It stayed like that until the boom of personal computers in the late 80s, early 90s. Alongside the explosion of mainstream PC popularity, there was also the emergence and rise of the enthusiast, including EK's founder, Eddie. Having the need to eke as much performance from their computers as possible, air cooling just did not deliver. They started to experiment with improvised solutions using what was available, such as garden hoses and aquarium pumps. As the years went by, this approach gained more and more traction, and it went from a novelty to creating a whole new branch of PC hardware. Fast forward to today, and now we have many providers of PC liquid cooling solutions for enthusiasts and professionals alike, without the need for them to raid the garden section of their local hardware store. As it is more complex, expensive, and involves liquids close to electronics, the majority of users tend to avoid it. But as technological advancements are enabling us to put more and more computing power into less and less space, we are reaching the point where liquid cooling's better ability to transfer heat will in some cases be the only option. For better understanding of what all of this means, we must first know what we cool. We mainly cool integrated circuits, more commonly known as chips. A chip is made from a large number of transistors. At its most basic, a transistor is an electronically controlled switch. Depending on if it is open or closed, this gives us the binary code value of 1 or 0. Computing instructions are then based on those ones and zeros, and how fast they can be executed depends on the number of transistors and the speed at which they can change state. In the 60s, one of the founders of Intel, Gordon Moore, observed that the number of transistors in integrated circuits doubles every 1 to 2 years. This observation inherited the name Moore's Law, and it still holds true today, even if the pace is slowing down a bit. To put this into perspective, the first Intel chip, the 4004, had around 200 transistors per square millimeter. In 1971, that was quite an achievement, especially considering it could perform almost 100,000 instructions per second, which was unheard of it back then. This is nothing compared to the latest 5nm technology, where industry leaders are nearing 200 million transistors per square millimeters. That is a millionfold increase in transistor density in just 50 years. Factor in the improvements in speed and increase in core count, we are looking at performance gains in the range of tens of millions. It is next to impossible to imagine how small a modern transistor is, as 5nm is just an arbitrary number. If we would place that transistor on a cross-section of a human hair and zoom right in, it would still be just a small speck. And on that cross-section, we could fit over 500,000 of them. We do not know how far the chip manufacturers can keep shrinking transistors and delving deeper into the quantum realm, making heat dissipation an ever-increasing bottleneck. So how much heat are we actually talking about? To know how much heat is generated by a chip, we look at the industry standard Thermal Design Power Rating, or TDP. This is the long-term sustained power draw of a chip at which the manufacturer guarantees the base performance. That, however, does not show the whole picture. The peak power draw, which is more or less equivalent to the maximum heat output, is normally 2 to 3 times the TDP value. Thus, something the size of a postage stamp has the thermal output of a small space heater. This, of course, means that even consumer-grade chips heat up very quickly. There is almost instant jump in its temperature to the level where the safeguards limit performance and prevent the chip from boosting any further. To an extent, this is also a result of better stock boost algorithms, which increase performance. Previously, you could only achieve this with a manual overclock. But whatever the case may be, the limiting factor is the cooling system. And again, here liquid cooling technology helps to overcome these limitations. Overcoming limitations and exceeding expectations is what EK does best. The attention to detail we need to maintain at top-tier products is second to none. The combination of cold plate geometry, block design, mounting system, basically everything must work together seamlessly to make sure that the contact is perfect and the heat transfer is as efficient as possible. Therefore, the whole block needs to work together flawlessly, which is a high technological challenge, as it is the connection between the heat source and the cooling medium. Coolants themselves also represent a high technological challenge. The challenge is how to make them stable, visually appealing, and at the same time efficient. In most cases, at least 2 of these properties cancel each other out. That makes our solid line that much more impressive, because it ticks all of the boxes. The biggest wow factor are the opacifiers, the suspended particles making the liquid opaque, which do not separate and settle even if the system is turned off. This is achieved by introducing an ionic charge into the liquid, permanently suspending the solid particles. This is, however, very susceptible to any impurities in the system. We know a clean loop is a must for the health of the coolant. To showcase this point, there is a display of solid coolants at EKHQ, where for several years now there has been no visual change in any of them. To help our customers achieve the same result, we are actively working on a solution, pun intended. What I want to convey is, if we look at the whole evolution of EK liquid cooling, is that you can easily see and understand the years of progress and innovation and how we have adapted to the challenges of the industry. Therefore, the underlying theme is, we never stand still and always innovate.
Standing still, I don't think that option was ever on the table. Well, as Blaž has made it clear, the industry itself demanded new technologies, and EK has been evolving since day one. Joe will tell us a bit more about the evolution of the cooling engine itself.
Throughout the single die era of CPUs, the fin structures of water blocks became denser and denser to deal with the increasing heat loads. In order to create a bigger surface area, progressively more advanced manufacturing methods were necessary. From conventional milling of simple grooves, to slit milling microchannels, and eventually skiving to produce extremely dense fin structures. Diminishing returns of blindly increasing the fin density drove us to optimize every single detail. Theoretically, the fin structure would have an infinite surface area while remaining completely open to the coolant. However, in reality, a compromise must be made to reach an efficient geometry that is practical to manufacture. To create an effective cold plate, there are several parameters which must be balanced for the application and material used. Taking any single parameter to its extreme would compromise the overall performance. One of the most significant variables is the ratio between the fin thickness and the slot width. A cold plate with extremely thick fins would be highly restrictive, thus reducing the amount of flow which the heat can be transferred to. By contrast, very thin fins would have a reduced effective surface area, as the heat has a smaller cross-section to travel through. The aspect ratio of each fin presents a similar trade-off. Short fins, while evenly heated throughout their length, have a small surface area to transfer heat into the coolant, whereas extremely tall fins cannot spread the heat evenly throughout their entire section. Assuming the flow is distributed evenly, that means less of it passes over the lower part of the fin where the temperature difference is at its highest, and the transfer of heat would be most effective. Typically, the cold plate is not evenly heated, and so the thickness of the material beneath each slot plays a very important role. A thin section would transfer heat to the fins extremely well, but only in close proximity to the heat source. On the other hand, an extremely thick base would allow it to spread perpendicular to the fins, engaging a far bigger surface area but at a lesser temperature difference. One breakthrough that would allow more restrictive fin structures to be implemented without a penalty to hydraulic restriction was to divide the flow domain. Introducing the flow in the center of the cooling engine and splitting it along two routes effectively doubled the cross-section. Combined with an impingement or jet plate to sustain high flow velocity, this quickly proved to offer a significant advantage. It was later adopted across all applications of high-performance water blocks. A significant drawback, though, was that the space inside the block had to be provisioned for the coolant to return around the perimeter of the cold plate, thus reducing the overall size of the fin structure in the center. Simply expanding the overall size of the block was not a viable option. While the cold plate could be extended beyond the IHS, socket specifications meant that it could not keep growing. Part of that limited space must also be provisioned for screws and gaskets. So with a split flow design, the fin structure was ultimately smaller than the contact surface. A recent novelty of directing the return flow over the top rather than around the engine permitted a single pass size cooling engine with split flow. Also, an inherently more symmetrical design meant that the flow was better balanced between the two routes. Most cooling engines considered that the heat was effectively spread by the IHS, and so the coolant should be evenly distributed. However, die sizes have become so small that this is no longer the case. Consequently, it was necessary to start targeting specific areas of the IHS with higher flow rates, thus allowing the entire surface area of the cold plate to be utilized proportionally, maximizing the thermal transfer. Furthermore, as individual silicon dies approach their density limitations and a viable core count, we are now seeing CPUs with individual chiplets. They are placed asymmetrically or even completely separated clusters around the IHS. Targeting those hotspots requires far more elaborate methods in order to bias the flow. A conventional split-flow cooling engine would not allow coolant to be introduced over every chiplet simultaneously. This is advantageous as the potential temperature difference is at its highest. Consequently, the flow can branch in multiple directions before being split directly over each chiplet. This ensures that the entire cold plate is used effectively. Then, the main challenge is to balance each branch, assuring that flow velocity remains high enough in every region. All of these factors combined allow EK to produce the highest performance water blocks, without compromising hydraulic restriction. Taking this efficient approach with every individual component ensures that the entire loop operates optimally.
Thank you, Joe. I think it is becoming clearer to everyone that liquid cooling is starting to be mandatory in server cooling. Despite density being one of the most important aspects, sustainability is an equal, if not more important factor, since the entire world is trying to take it to the next level. I will now invite Blaž to tell you the details about how liquid cooling can bring that sustainability and reduce energy consumption. Blaž, take it away!
Sustainability is becoming an ever-increasing consideration when designing new products. There are two components in sustainability. One is a rational use of resources in the product's lifecycle, and the other is a reduction of energy consumption compared to alternatives. Technological advancements and modern consumerism drive people to buy new things before they actually reach the end of life. This then puts responsibility on the manufacturers to ensure the responsible use of resources. Rational use of resources is also one of the biggest innovations in coolants, which is in the final stages of development. It is a certified bio-based coolant with 98% of it made from renewable sources, and it will be the first coolant of its kind in the world. Another good practice are EK blocks, which are mainly constructed from materials which can be recycled an infinite amount of times without losing any of their physical properties. I am of course referring to copper and aluminum. The other advantage is also the use of non-permanent assembly, which not only allows servicing and therefore longevity, but the complete separation of parts for maximum recyclability. Block recyclability is important as the active life of CPUs and GPUs is only a couple of years before they become obsolete. This is because of the aforementioned technological advancements, which drive consumers to replace otherwise working equipment. Although technological improvements have slowed down a bit, releases of new generations of products are nevertheless becoming more frequent. This is why this is still the main driving force in the consumer computer hardware market. As the blocks are product-specific, it is very important that they can be recycled as much as possible to limit the environmental impact at the end of active life. Other components in the cooling loop, such as fans and pumps, due to their function, cannot have this recyclability integrated. From a sustainability standpoint, this has to be tackled differently. These components are not that susceptible to technological obsolescence and can be used continuously even if the computer hardware and specific blocks are changed. This is why we ensure that the life expectancy of these components is as long as possible, thus reducing the resources needed for the overall manufacturing. For example, it is relatively rare to use ball bearings in cooling fans, but we do. The fans are therefore more expensive and comparably a little bit noisier at lower speed, but the trade-off is a far longer life expectancy compared to their plain shaft bearing counterparts. Another major element in the loop is the pump. To make sure our pumps last as long as possible, there is a test running at our facility to evaluate their life expectancy. The tested samples have been running continuously for over 3 years now, at full power without any faults or measurable wear. This means our consumers have a quality product that can, in normal circumstances, be used for many generational changes of other computer hardware. The second benefit of liquid cooling in terms of sustainability is energy consumption. At the first glance, liquid cooling does not have any significant efficiency gains. Most of the electrical energy used by a computer is transferred into heat anyways, which needs to be expelled one way or another. If the computer is used for non-complex everyday tasks, then the power draw of two identical setups, either air or liquid-cooled, will be very similar. But when the computer is pushed to its limits, for example while gaming, rendering, video editing, 3D modeling, etc., then liquid cooling shows its benefits. Manufacturers usually specify the maximum temperature at which a chip can still safely operate without any long-term damage occurring to it. That is fine, although it has been proven that running electronics cooler does prolong their life expectancy, mainly due to thermal fatigue. There is another hidden fact, which is that the efficiency of a computer is inversely proportional to its operating temperatures. The hotter the components, the less efficient they are. This is because of two phenomena. The first refers to conductors and their internal resistance, which resist the flow of electricity. An electrical current is in essence the movement of free electrons, which are hindered by the oscillations of atoms in the crystalline structure of the metal. As collisions between atoms takes away energy from those electrons, the higher the vibration, the more frequent and stronger the collisions. As the intensity of atom oscillations is what we measure as temperature, the lower the temperature, the lower the resistance, and thus higher the efficiency. In semiconductors, such as silicon in computer chips, the phenomena of electron flow being dependent on the temperature is somewhat different. Without going into too much detail, as some of you with a physics background know the specific best, the reason why the power consumption in semiconductors increases with temperature has to do with the current leakage, which increases with temperature and voltage. This phenomenon is known as the Poole-Frankel effect. This is all well and good, but what both of these effects mean is that a computer running at lower temperatures will consume less power. Coming back to liquid cooling and its far superior ability to take away heat, it enables the computer to run cooler or enables higher performance with no additional cost to power consumption. How much power consumption can be lowered is very difficult to generalize, and it depends on so many variables such as CPU and GPU type and brand, the workload, and so on. Based on a limited number of tests, running a fully loaded CPU at 60 degrees centigrade versus 90 degrees can result in the whole system using 5 to 10% less power, which is not insignificant. An even bigger impact on sustainable computing can be made in data centers, considering aforementioned efficiency gains, and the data centers use a huge amount of power. To put some figures into perspective, the US, having the most data centers, in 2017 used over 90 million megawatt hours of electricity to run them. This represents 2.2% of the whole energy consumed in the US that year, or in other words, the equivalent of 24 million average European households. There is also an elephant in the data center, which is that older centers represent just 1/3 of facilities and consume around 2/3 of the power, yet only contributing 4% of performance. And with the increase of cloud computing, artificial intelligence, data acquisition, and more, this discrepancy is only expected to rise in the upcoming years, although not as much as it was anticipated a decade ago. Therefore, if we can improve on efficiency and reduce consumption in data centers for just 10% by possibly using liquid cooling, we would free up enough electricity to enable the transition of almost 2 million vehicles to electricity in the US alone. All this clearly shows how liquid cooling has a massive sustainability advantage compared to classic cooling solutions.
Sustainability is a part of EKWB through and through. In addition to a rational use of resources in products' life cycle and the reduction of energy consumption compared to alternatives, EK also strives to extend the use of our technology elsewhere. Sandy will tell us a bit more about the necessity and the potential of using liquid cooling with server components in desktop systems.
There are a lot of companies offering workstations, either air-cooled or partial liquid-cooled when you have AIO for CPU and air-cooled GPUs, but there are only few companies that offer fully liquid-cooled workstations. Majority of them offer custom liquid-cooled systems. Of course, EKFluidWorks falls under fully liquid-cooled systems with upgradability options and custom-developed liquid cooling. Despite going all in with liquid cooling, we took it one step further. On our X7000 series, we use server-grade motherboards, which at first glance is nothing special, but we went there to increase performance and reliability. When talking about 7 GPU systems, and when you want all the cards to perform at 100% utilization, server-grade is the only way to go. Now you're probably asking yourselves, why is he mentioning this, right? Going to server-grade motherboards brings a lot of challenges, especially when you are using them for desktops. We are encountering no or poor pump or fan control support, no support for USB, as the ones on the board are mainly used for the configuration, and no sound modules. And of course, I think we all agree that these things are mandatory on desktop systems, right? Since we know that these are a must, our partner XenoWolf developed all of that. Let me share some words about pump and fan control module. It's totally autonomous and independent from your operating system or hardware. In other words, it does not need any operating system to run. This is really important as we are offering different operating systems and variety of configurations. As the unit is measuring inlet and outlet temperatures of each radiator, it knows if it makes sense to increase fan speed or not. The same goes with pump speed. We can say that there is a certain level of AI in the unit. The AI learning process took a long time until we got to a perfect ratio between noise and cooling performance levels. What I can only say is that the end results are extraordinary. We added a removable, detachable Wi-Fi module on it so you can connect with any mobile or remote device. This module is detachable as sometimes remote connections are forbidden, so we did not want to embed it into the main board. Every unit that is connected to the module is monitored and controlled separately. Pumps, fans, temperature sensors, flow meters, and if any of the connected units starts to behave normally, the module is able to send email to the user or support that there is attention needed. This is really important as you will know that something is happening and can react before it causes a complete shutdown of the system. When we compared the control of cooling systems from non-server motherboards to how our module is controlling, it convinced us also to implement this module in our Studio series, the S5000. It is just so much better that it was no-brainer for us to add it. Additionally, this unit is also suitable for controlling the server cooling, where it's really a challenge to connect all different manufacturers and control cooling systems independently. I talked about how server boards do not have USB connections for desktop users and have no sound cards. We covered that as well and developed a second board that enables sound card and all the latest USB connections on front panel of the chassis. In addition to that, we added USB ports on the board itself so you can attach software license key or dongles inside the chassis so it's not visible and in danger of getting lost or stolen. The key message is that in addition to other engineering work, these products are a perfect example of what XenoWolf brings and what powered by XenoWolf means for the customer. I will hand it over to Santa and be back in a second.
Sandy has been talking about the challenges of using server components in desktop systems, but we're also actively involved in the automotive segment. This can create a lot of specific types of challenges, so I would like to invite Sandy back to the stage to share some insights into automotive solutions.
As we have been talking lately about automotive-grade water blocks and them being in the final industrialization test phase, we would like to give you some more details about the reasons why EK took the path to automotive readiness. Okay, you're probably asking yourself, why did we go there? We have been present in the automotive segment, mainly autonomous vehicles, for many years now, and we have been developing and manufacturing cooling solutions for our customers. Since we have been supporting them from the early times as startups, we took it a step further and didn't only think about the startup phase, but looked into the future, including series and mass production. We knew that the products that were meant for a steady state, like desktop computers, cannot stay alive for long in harsh automotive environments, due to temperatures, vibration and shocks, and in order to withstand them, the products have to be made differently. So parallelly to our customers testing and validating their systems, we introduce manufacturing technologies that are suited for this kind of usage. And one note, in order to say that a certain product is automotive grade, it has to pass all prescribed tests in laboratories. Main goal in the development we had was no screws for better vibration resistance, no sealing gaskets for lowering risk of leakage, easy to use for customer, less assembly parts, less queues to work with, and at the end, high volume production capabilities. Firstly, we looked into technology that is already widely used and field proven in the automotive world, brazing. We reached out to our automotive partner that is very experienced in brazing technology, and together we developed a brazed water block that perfectly covers all the points that I previously mentioned. We combined EK's knowledge of cooling solutions with our partner's knowledge of manufacturing brazed product, and we came to a final product that is near indestructible. We optimized the cooling engine so the fins are not too dense, so the block is not acting as a cooling loop filtration unit, but still did not significantly jeopardize the cooling performance. I mentioned high-volume manufacturing capabilities, right? Let me tell you, the installed manufacturing capabilities are at 4,800 pieces in 8 hours, which is more than enough for now. As everything has its weak points, brazing technology is no exception. A relatively high MOQ, due to tools needed, limitation in geometries, led us to further investigate different technology that could be added. We reached out to a leading German company for laser welding, and together we developed a laser welding process of aluminum, which covers all the important topics that brazing does, but it's not so limited with shape, and we can also weld lower quantities. Both technologies will be developed further as we want to widen the scope of their applications, especially brazing technology for mass production with the focus on economy of scale. This is it, guys. I just need to say one more thing. Brazing and laser welding are only the beginning. We are exploring and investing a lot into other technologies, so there is still a lot to come. Stay tuned, but that's it for me. Thank you.
That's right, Sandy. Brazing and laser welding are only the beginning. But as Sandy mentioned, in order for us to use certain technology, we need to be sure that we can control the outcome that these technologies bring. We need to be able to give the best quality assurance possible. Franz will tell us a bit more about how we can take care of the quality.
There are two important factors of assuring product quality in EK. Top-notch technical solutions that were mentioned previously are definitely one of them. The other one is the EK way, our principles and way of work. And I really enjoy talking about our processes and methods through which we strive to achieve excellence. In assuring quality at EK, we don't rely only on the final quality control. We have started incorporating quality in every element of our company's operating system. We do our best in providing a frictionless experience for our customers from their first contact with the EK to the end of the product's lifecycle. There are 4 elements of assuring quality. The first one is the product design, where the design, failure mode and effect analysis is used to detect and evaluate potential defects in a product before it is even finalized. On the grounds of past experience, we construct robust products resulting in easy assembly and high first pass yield. State-of-the-art materials and surface treatments are selected and used to ensure longevity of our products. We run stress tests on prototypes of our future products under controlled conditions. The second element is material quality control. We control all aspects that influence the quality of the product. We build long-term cooperation with established suppliers. We validate first samples of materials and release them for production. The third, our production and proficiency of production workers. We use a systematic, proactive method, which is process failure mode and effect analysis, to define the assembly steps, anticipate risks, and eliminate them early in the planning phase. Do it right the first time. We follow this principle to minimize interactions with delicate components in production. We manufacture hundreds of different products. It is essential that we train our production workers constantly and focus on their engagement. They maintain their high qualification level and build multi-skill proficiency. At the end of the assembly, all parts must go through final control to make sure that every product leaving the house is safe and performs flawlessly. The fourth quality assurance component is continuous improvement. We keep contact with our community through our presence on social media and strong technical support. When our products hit the market, we analyze continuously what is happening with them. In small, agile, multidisciplinary groups, we rethink our past steps to achieve better results in the future. We increase our competences by cooperation with the best knowledge hubs. With them, we analyze causes of deviations, find solutions, and implement them.
So, this is the magical world of liquid cooling, where we're pushing the boundaries and elevating computers for the better world. Cooling is such an integral part of computing that we felt the urge to share our knowledge in order to accelerate our collective progress. As things move at such a rapid pace, we anticipate even more challenges in the near future. To see what we have on the table and to become part of our vision, please subscribe on our Technology Day page. That wraps up our first Technology Day. Stay informed.
Let me just say a big thank you to all our guys. As always, you are awesome. Now it's your time to ask questions. So if you have a question that we didn't cover, please join us for the Q&A section. I will kick it off with the first question. After we saw all the new areas that we're looking into, will we still be devoted to developing DIY components?
Absolutely. EK is a technological company driven by the community of hardware enthusiasts. Technology, innovation, and passion is our motto. We will push the limits of cooling together with our industry partners. to deliver the highest semiconductor performance possible. Stay tuned!
Welcome everybody to the Q&A section of our first Technology Day. Hope you found our content interesting and you learned something new. For the beginning, here with me is Sandy Logar.
Hello.
So any questions directed to his content, especially the automotive sector and on the server side, feel free to put them through. And already we have one question, which we can start with. So you develop special boards which can be used like server motherboards on desktop systems. So why do you think competition is not taking that path?
You know, I say first of all, hello everybody. Thanks for introducing me, Blaž.
Yeah, sure thing.
So yeah, first of all, it's not easy. And going that path, of course, we are technology. We are becoming technology leader. We are already on the field of, would say, custom liquid cooling, and we want to do that as well on the other fields as well. So that's the thing why we decided to go there, because anyway, these are our high-end systems, and it's normal that if you are looking at it's not high. This was developed for high-end system, and it's normal that this will not be in the high volume. It's not a high volume product, and in that case, it's normal if you're looking for just from the economical way. Why to go there? There is no financial economical part why to develop.
There's no benefit for that.
No benefit, of course.
Sure thing.
But we decided to go there because, of course, we are using server grade boards. We are developing this because we want to be unique. And with these boards that we developed are now what we did. This computer works. I would say the control system works really perfectly. And what we do now it's everything is tested on the high-end machines, and we are now working the way of trickling down, perfect trickle down system. That means that we are now we are trying new things. We are trying new things on the high-end systems, and then when it works, it performs, we go back to develop it, to bring it further down the stream. And it's normal that, let's say, competition is not going there because there is no volume behind it. That's basically, and because it's not easy.
So we're doing something to actually elevate technology.
Elevating computers.
Exactly. One thing that I need to mention as well right now, so any questions regarding the cooling engine and also the quality, Franz and Joe will also be joining us later. And the next question we have for Sandy right now is, you were talking about AI learning process on the pump fan module. So it's taking a long time. Can you say a few words about the process itself?
Yes, the process itself took more than 6 months. What we did together with our partner, we started a system, our high-end system with 7 GPUs inside, torturing it for 6 months and measuring everything, what's going on with the system. That means what's going on with the coolant temperature, how everything reacts, how everything reacts when you change a little bit pump speed, a little bit fan speed, and we gather all the data. There is a huge amount of data behind it. And now the AI, and then with the AI learning, we knew the system knows exactly. Okay, when you raise pump speed for a certain amount of RPM, what happens?
So that was actually the machine. So it was actually machine learning. So the AI was happening with the computer. It's not somebody that was actually looking into the data and writing.
It was the AI. It was and our partner Xenowolf wrote the software for that starting. So and then this is why everything took so long. But now really I must say that like I said, the end results are extraordinary, and it really a no-brainer to put it also on the I would say mid-end systems. and we are still evolving it further. So it's
So I'm guessing it's also beneficial because it adapts to the configuration of each individual computer.
this is what we are doing now. Especially now we are testing it throughout the complete. Let's say, of course, we have majority. There is a lot of operating system, different systems, different hardware, and so the process is still running. So now we are doing it on the known configurations. And we are evolving it constantly.
Perfect. Next question would be, is you were also talking about the Wi-Fi module on the control. So it's removable and sometimes it's forbidden to have any remote connections available. Why is it forbidden?
Yeah, when you have anything, let's say when there are certain customers that are working the field of, let's say, when they are working with classified information, there is definitely forbidden to use any.
So the system must be completely off the grid.
Oh yeah, so it's off the grid. So any possibility, slight possibility that you can connect to the unit remotely, you have to eliminate that. So we did it. We have it's detachable, the module itself. So we said we will not have separate board for that. So it's up to the customer. So when they say we don't want to have that, we just pull the module off and that's it. So it's hardware. It's disabled with hardware. So we cannot. It's not just software behind it.
Yeah, yes. It cannot be overridden if it's not there.
No, it's not there. Correct.
Sure. So there's another question about the pump fan control. Will it be available as a standalone product?
Yeah,
consumers?
that's, I would say, never say never. That's the first thing. But what we are, like I said before, we are testing it now with variety, with different configurations, because when you bring this product to end customer, to the retail, so it has to be really flexible. It has to work with every configuration that's available there. So this is what we are working on now. And now when we are doing it for our workstations, it is, let's say, well monitored, so we know the exact configuration, we know how it behaves based on the operating system, based on the hardware configuration. So when we are solid with that, I would say, but for now, we are in this testing phase and we want to have everything under control because, again, putting something on the shelf that we want, it's solid, otherwise we'll not put it. So it's solid for all variety because you never know the end configuration then or end user. So we have to prevent, or predict everything before it goes to the shelf.
Yeah, and this also kind of ties in with the next question, which kind of falls into my category, what I was talking about. Is controlling and everything, how much cooling we need, and also how much power can a high-end desktop CPU actually draw. So I can answer that one. When I was doing research, I was looking at a top-end previous generation, so the 10th generation i9 10900K. And the interesting part is it actually draws for a short period of time with stock boost algorithms almost 300 watts. And that's a lot of power, and if you do a manual overclock, you can actually get it to go over like 350-ish watts as well. So this is putting a very high demand on the cooling systems. So this is this means high demand on the cooling system, and also with the pump control also, so you have cooling and also control as well.
Yeah, the one important thing with this model is you will never have these immediate bumps up and downs in temperature because we are monitoring input and output of each radiator in the let's say when you're measuring that, you see how it behaves, so there is no bumps, nothing, so it's really stable.
And also one thing besides that, so in conjunction, so everything together with the liquid cooling as well, so the added benefit of liquid cooling, apart from its better capacity of taking away heat, is also the whole capacity of taking that heat in, so you don't need to have that immediate bump in the fan speed, so you can have that little bit of a delay when you have those short spikes of the high demand or high power draw.
Yeah.
Okay, so if we move on forwards, the next question is actually referring to the automotive part. So for brazing technology, you will have products available soon. What is the development time and start from the design series production if a customer reaches out and wants a new product?
Yeah, that's basically when I've been talking about the plus and minuses from between different technologies. I would say for brazing, roughly, I would say around about 6 months from day zero, from launch to then you have development cycle, then you have all the tests and everything and production setup. That's the longest part, I must say, because there's a lot of fixtures to do and everything. So I would say in 6 months you can get product I would say specially developed for you if you need it. And then let's say we can start serious production with it. Of course, this is the best case scenario. So if there is a certain optimization loop needed because of any reason, either it's part related or anything, there can be but I would say in 6 months we can be with parts. You can have parts from the serious production.
So this is for brazing.
This is for brazing, yeah.
So what about
laser welding?
Laser welding.
Laser welding, it's a little bit faster because the basis of the material, the basic of the component is you can mill them, so we can be faster with that. So I would say for laser welding it's about half of that. So I would say in 3 months we can have parts available laser welding technology. And also, if you want to have automotive grade, we can do first step with laser welding, and parallelly we can do the brazing for higher volume production. So you still can validate everything. And still have the automotive grade, I would say, block available for you, and we can combine the technologies for this to speed up the test cycle.
So this is going to be my question then. When you're talking about automotive grade, what is automotive grade? So this means that it has to pass certain requirements in laboratories in the field.
Correct.
So can you elaborate on that?
Yeah, of course. That's good. Thanks, Blaž, for asking that. Usually forget about that. So yeah, when you say that something is automotive grade, it has to really pass all laboratory tests. And first is, of course, vibration and shock. So what we are doing, we are constantly working with our, I would say, local certified laboratory. Laboratory, when we have all the vibrations, let's say when they do. So what we do, we have of course the profiles, everything written. So we have the procedure that we have to follow, and we are testing the shock and vibe tests in all directions. That means X, Y, and Z. So that's the first part. So mechanically if everything will still be together, because you cannot believe what happens to the part after vibration test. You're surprised.
Yeah.
Usually. Okay, not now. We are getting more and more experience, so we are not that surprised anymore. The second part is of course corrosion. Corrosion is one thing that really when something is used in the car, it gets let's say either it gets in contact with different chemicals that could be there is salt on the road. There are let's say windshield cleaners. There is brake fluid inside. Everything and in combination with. So that's the part. So everything has to withstand also this part, that's corrosion part, and of course one that we are doing it internally. We have the climate chamber, so all the fluctuation in the temperature, so either high heat, really freezing below freezing point, high humidity, low humidity. So all these tests are done. So these are the three main things that we do. Of course, there is a lot of small things, so it has to pass everything. So this is how we are. But now, when we are getting more and more experience, of course, the developed part is already developing that way. So we just maybe have to do either there is a certain customer requirement, even higher demand. So we do that test as well. But on basis, we know what to do so that it passes the I would say automotive readiness.
Yeah, it kind of has more parts than you would think at first glance. So I'm looking at this, and I think that's we come to the end of the questions regarding what you were talking about.
So yeah, I would just then just say anything that you still remember about it. Of course, all the questions that you will post later, we will answer them. No worries. So now no question will get lost or forgot to be answered. So anything related to either FluidWorks, either to I would say the control model or anything automotive related, please reach out to me. I will be more than happy to answer.
Yeah, Sandy, thank you very much.
Thank you.
Thank you for all of your insights. It's very interesting because, like I said, it has so many layers, all of these topics. So I would like to thank you again. And
Thanks, Blaž, for hosting.
Sure thing, yeah.
Thanks, guys, for listening, and stay safe.
Yeah. The next person who will be joining me is Franz. Franz is head of quality. And the question for you is, first of all, welcome.
Hello, Blaž. Thank you for having me here.
Sure. I think it's for everybody. We're having everything, so now we want to elaborate on what we were actually talking about. And the first question is, and it's really on point because we are talking about tech days and we are talking about quality matters. Why is that?
Quality and innovations or technology, for me, they go hand in hand. Because you can take innovation by sporadic actions only to a certain extent. And you need a system, a management system, similar like to quality management system, to streamline activities of innovations to bring out the best result.
That is true. So yeah, some might say that the pursuit of bigger quality would kind of hinder innovation, but I don't think that's the actual case.
Not really, because quality and innovation, they work in the same. They are striving for the same goal, to make our customer for the satisfaction of the customers.
And also continuous improvement, I guess. Yeah, this has been kind of floating around a little bit, and yeah, I also want to clear the air with this one, so it's quite on point. So, quality of EK products has worsened lately, according to social media posts.
Yes, the number of failures on the field has risen, and the number of RMAs has risen, and the reason for this increase is our significantly higher output from our company. So consequently we have more failures on the field and more buzz on social media. But actually, if you have a look at the percentage of failures from the field, and if you compare it to our output, the percentage is lower than last year. But this is no excuse. We still have to work on constant improvement of the quality of our processes and the quality of our products.
Yeah, I completely agree. That is true. There is a sort of perception that it is. But there is also have been quite a lot of screw standoffs missing, strip broken, untightened on the field. How are we handling this?
So we noticed this failure that it was quite often happening on the field, and we analyzed the RMAs, and we found out two root causes. The first one is that the material of screws is really not as it should be, and the second one is that the customer were using wrong length of the screws for fixing their graphic card. So we have established now a group, interdepartmental group between quality and R&D, and we have to revise the quality of the fixation material generally through the company, and set the tests which our fixing material should undergo successfully. And the second, about the wrong length of the screws in our in the material which we will place with our blocks. In the mounting material, we will separate the length of the screws. We will divide them and mark them accordingly. So we will simplify the assembly of the customers.
And also improve the user experience, and also
Yeah.
take the, let's say, mistakes out of the
This is the
equation
main
as
point,
well.
yeah.
Okay, so one question here is kind of going into this one, and I think this is more from my end, is talking about different mounting different parts of the block. Is the percentage of a typical block, how much is it recyclable? So as also was shown in the initial video, is more than 90% of that is recyclable, because mostly it's made out of materials which can be infinitely recycled an infinite amount of times. So the only things that are left is the rubber seals and also any electronics in there. So that is the part that cannot be recycled. Everything else can be just disassembled and recycled in any each way. The only thing is, it's on the consumer to be diligent and to actually, when they stop using the product, is they actually disassemble it and separate it into individual parts.
May I point out that
Sure.
In the past we were considering trading in. That means that the customer could send us back their used products, and but we found out that financially it does not work out. So, but as you said, our products are to a very high percentage they are recyclable, and it is up to customer to
The thing is, I remember that as well. It's not just a question of the financial aspect of it. It's also the question of when you're talking about the sustainability. If you would ship a block halfway around the world, you're actually diminishing this. So it's just better to do it where it is.
To surrender it to the local facility for cycling.
Yes. Coming back to quality, there has been a little bit of talk about nickel plating. So how do we check the quality of the copper base and the nickel itself?
So we use a special electrolytic process for nickel plating of copper bases, and this technology was proven to be the best for the environment in which our product operates, and also for the chemicals with which our product came in contact to. So we do nickel plating at our subcontractor, and we assure with standardized tests that the nickel plating process is carried out perfectly, and also that the nickel plating is of agreed thickness.
Sure. Yeah, also one question that is also kind of going into both directions. So one thing I was talking about, so sustainability and quality, is which pumps are being tested in the long-term tests. So yeah, back at HQ we are performing the long-term tests. I think I'm right in saying it's been running for over 3 years right now, to make sure that those pumps are as best as possible. So both in terms of quality and longevity, and the pumps we are testing are the VTX series. So the VTX series pumps are the ones that have been running 3 years non-stop, full power, and this is how we are ensuring that they last for many years, and they will not contribute too much to the ever-increasing problem of e-waste. And coming back to you, Franz, and the last question is we are also, so the blocks need to, we need to make sure that they are performing as they need to be. So one of those things is also making sure that they do not leak when they come to the customers. How do we make sure that happens? So basically a leak test.
So every product leaving the house is checked for leaking. We use special, very precise, calibrated testing equipment at the end of the line. And for each product group, we have their own tolerances, or their own tolerances according to which pressure the product should be tested. So there is a filling phase, there is a settling phase, and then comes the time window in which our products are checked for the leakage. And the tolerances for leakage are very strict.
And how long does that test usually last?
It depends on the product. It could be from 15 seconds and up to 90 seconds. It depends on the product. And also the parameters for testing, they depends on the product group. For let's say for the loops are different than for the radiators.
Sure. Okay. So thank you very much. It's been very informative listening to things that go behind the scenes, especially when the current situation regarding the social media, as was also mentioned here, is as it is. And I think we kind of hopefully calm down some of our customers as well, because we want to assure them that we are working our best and we are doing everything that we can do to make sure that you get quality products. Yeah. So Franz, thank you very much for joining me here.
Blaž, thank you. Yeah. Thank you for your attention.
The next person who'll be joining me is Joe. You know him very well, especially because we're going to be, I think it's going to be interesting because we're going to be talking about the technical aspects of things. So, Joe, thank you for joining me.
A pleasure.
So one thing is, we were talking about smaller fins and slots and everything. Why don't we use smaller fins and slots?
So, fundamentally, we believe in pursuing a balance, not just continuing to increase the density as far as we can. And there's two reasons. If we make the slots much smaller, that will, of course, increase the surface area over the whole block.
Yeah,
but with that surface area increase, will also increase the drag on the coolant. So a very small channel would have higher restriction, and consequently, it would also collect contaminants from around the loop. It will cause problems elsewhere, and a similar story is true of the fins. So the fins themselves, the thinner we make them, the harder it is for the heat to be conducted to the top because the cross-section reduces. And then, in effect, even though it seems like we're adding surface area, we're actually reducing the effective surface area that has a big enough temperature difference to put heat out into the coolant.
Yeah, and I'll put my 2 cents here is, okay, we are putting more restrictions into the whole engine, but why don't we just use then more powerful pumps?
So really simply, if let's assume that the pump was exactly the same in both scenarios, so the pressure from the pump was equal. In the case of the more restrictive block, this would lower the flow through that part, which would be an issue in itself. Okay, but we could optimize it to get over that. So if we make one CPU block that can deal with a lower flow rate, it's not an issue. However, this also affects the radiators. This also affects every other block in the loop. And to reduce the flow rate there, we start to disrupt the balance of the system, and it's not worth making one single product highly restrictive, because it may look great when you see that product on its own, that it has great performance, But when you put it in a loop with other parts, and there's a unlimited
And there's just so
Unlimited
much
number
high, there's just so high we can go with pressure and flow.
exactly
Yeah. So also when we were talking about different elements in the loop, so basically the main two are in terms of cooling are the GPU and CPU blocks, and the question here is how are the two engines between the two different?
So in the very early days, they were actually similar. The requirements for dissipating heat is exactly the same in both scenarios, but as time goes on, GPUs have grown much, much bigger. So even though they're getting denser, they're using finer manufacturing process. The die of a GPU is huge, and the heat is really well spread. So the cooling engine can spread across it, and there we want to distribute the coolant as evenly as possible. Typically, they don't have an IHS, so we don't have to worry about how that heat's laid out. Whereas on a CPU, there it makes sense to start to concentrate on where the heat is coming from, because although it has an IHS, the heat load is not spread perfectly like it is
Yeah, especially
on a GPU where you contact
with the new
die.
one with chiplets as well. Also, it's kind of
And that, yeah.
and considering that, this is a question more from my end, also connected with this having the balance and the lower temperature. And I was talking about longevity of components, and I mentioned thermal fatigue. So the question is if I can elaborate on that one. So yeah, the thermal fatigue is basically referring to cracks appearing in the solder between connections from the PCB to different components, so from the circuit board to different components. And this happens when you have a great temperature difference. So when you're heating the system up, you have different temperature expansion and contraction depending on different materials, and how much it contracts or expands depends on a component. And this is basically different between the PCB and the components, and then you have this difference. And the higher the temperature difference, then more of this difference then actually accumulates in those solder connections, and you have then small fractures appearing, and those small fractures through these cycles get bigger and bigger and bigger, and then eventually it can happen that the solder connection breaks entirely. So this is why keeping those temperature differences as low as possible is the best possible solution to make this sort of phenomenon of thermal fatigue as little as possible. There is also a possibility, well, with DIY solutions. So some people are actually putting those boards when they have a broken connection. They're putting them in ovens, heating them up, so the solder actually gets kind of melted away and then reconnects. But that's a touch and go, and it could solve the problem or it can destroy the component completely. So our suggestion would still be, from our perspective, is that liquid cooling is still the best in this case of keeping this temperature fluctuations to a minimum, and this meaning that the components would last as long as possible. And also going back to the technical sort of side is when we're talking about PCB solders and everything, is also the materials. We're using mainly copper, and is copper the best material for cold plates?
That depends entirely on the perspective of the user and the scenario where it's used. If the cold plate is engineered with the material in mind and all of the parameters are optimized for that material, the difference is surprisingly small. Only a couple of degrees between aluminium and copper, for example, and then a step beyond that would be silver. Solid silver brings a really negligible gain for the amount of expense added. So mechanically, aluminium is really nice to machine, and for that reason it's probably the best price performance you could get from a cold plate. But in the eyes of enthusiasts and the majority of our customers who buy individual components, copper will always be the king, simply because of its compatibility with other metals, with brass and stainless steel, and it allows you to have an extraordinary diverse loop.
Yeah, when you're using just if you're using aluminum in blocks, and then you're kind of restricting yourself what you can use for other things. Yeah. So what can we expect for the future of cooling engines?
Nice. I think the next advancement that will take us forwards is 3D printing, and the ability to make both cooling structures and cold plates that have blind geometry. So the channels would be inside and completely sealed, and then they could also take forms which are completely oblique and not possible to cut with conventional tooling. I think that will make a big difference in how we can very delicately place where coolant goes, how close it gets to the
more
to
intricate
the
shapes
IHS,
and everything. Yeah, and the thing is, the technology is as everything. When it's a novelty, when it's new, it's expensive, but the prices are going down, and it can then trickle down into the mainstream market as well. So yeah, that is an interesting point with that one. So that is sort of a future we can look forward to. So I think that's the end. So we are nearing the end. Joe, is there anything else you would like to add from your side?
From my side, it was great to be a part of the first Technology Day, and I look forward to many more.
Yeah, so do I. So I would like to thank everybody for joining us for this a little bit over an hour. So also, if you liked our content, please subscribe, follow us on all of our social medias. We're present basically everywhere. And again, thank you very much for your attention, and hope to see you on our next Technology Day.